if we are looking at combustion, the combustion is basically just an oxidation reaction.
Correct.
Yeah, but we also have something like corrosion. We can characterize corrosion also as an oxidation reaction.
Correct.
But the two are different. Okay, although maybe the fundamental chemistry behind them is similar. So how would you differentiate between them?
See, if you look at, let's say, combustion, it is basically an instantaneous exothermic reaction. Where, let's say, methane reacts with oxygen. Very important, again, to mention over here that all this happens in the presence of an activation energy. So there is a spark, there is a flame which actually ignites the fuel and air mixture, and then you produce heat, light, and the products of combustion. So this is an instantaneous process which is exothermic, and then we are able to harness it. Whereas if you compare it with another oxidation reaction which you mentioned, which is the corrosion aspect of it, rusting of iron. Yeah. So rusting of iron is such a slow process. So you have iron, presence of water, and presence of oxygen. The rusting takes place over a lot of time. Yeah. So I wouldn't put a time frame on it, but it happens on a layer to layer basis. Yeah. So whatever layer of metal is exposed to both water and oxygen, that gets oxidized. So that layer is formed. It starts flaking over a period of time. The moment the flake is removed, which means the entire surface is now exposed to newer corrosion. So if you look at it, the end game is the entire metal piece is going to disappear. Yes. So there's going to be nothing more left. But the process is going to take a long time. Yeah. As opposed to that, we're talking about a process which is much more faster and which can be harnessed for our day-to-day lives.
Yeah, that's an interesting. So basically, the time frame. So there is no potential for us to harness energy effectively from most of the corrosion processes. It's not something that is.
In fact, we try to prevent.
Right. Yeah. And the corrosion is actually detrimental when it comes to the material associated with most of the industrial equipment. But yes, this is the fundamentals behind it. Yeah, we are looking at the stoichiometry aspect, the oxidation aspect. Yeah. If we want to connect that to the practical side of things, if we are looking at combustion, so I, for example, learned about the stoichiometry in college. Okay. But when I look at the industrial burn process, there are a lot many additional parameters that need to be accounted for, both in terms of the control and the safety aspects. So how would you basically take it from that classroom learning to an industrial application?
See, when one looks at an industrial burner, I just cite an example for a gas-fired burner. So you have basically gas entering at a certain pressure into the burner, and you have oxygen. This oxygen basically is nothing but the oxygen which is present in atmospheric air. This is driven into by a volumetric device which is nothing but the combustion blower. Yes. So which is in most of the cases part of the burner itself, or it can be otherwise depending upon the configuration of the burner that we choose to install. So you have a air to fuel mixture and mixing taking place in the chamber. Okay. Right. So when we are talking about a boiler, so essentially you have a furnace. So the burner is mounted on the furnace. So both the fuel as well as the air, which is nothing but the combustion air, are thrown inside the chamber, and in the presence of a spark, which is nothing but the activation energy. Right. So it catches fire. And the combustion process from there on is controlled. How do we control it? The flow of gas is controlled. Yes. So we are able to control the flow of gas. The flow of air is controlled. So we are able to control the air to fuel ratio itself. Yes. So now the control of the air to fuel ratio gets the dimension of the efficiency, because by controlling the air to fuel ratio, we control the excess air levels. We are not allowing the excess air levels to go either this way or that. If it goes lower, then we have a problem of incomplete combustion and hence a loss of efficiency. If it goes higher, then we have a higher stack loss and hence a lack of detriment. It's also detrimental to our efficiency. So these are the aspects which are taken care of by the burner. Another important aspect which is built into the burner itself is that the air to fuel, the air and the fuel are basically blown inside the chamber in a certain pattern. So this mixing, what you spoke about, this mixing takes place within a confined space, but the pattern is such that within that confined space, I am able to give a longer residence time for, I am giving a lot of chances for the air and the fuel to mix.
Yes.
Because I want the entire combustion to take place within the confines of the furnace itself. I don't want the combustion to take place inside the chimney. I want the combustion to be limited inside the furnace itself. And after the furnace, what I want to see is basically nothing but flue gases.
Yeah.
I don't want to see the flame get out of the furnace. So those are the aspects of control that I wish to exercise. And I am able to exercise with the burners that we speak about. There are other limiting factors. We spoke about the limiting factors like the flow of oil, flow of gas inside the burner, flow of air. That is also something which is limiting. So now we have a lot of instruments like measuring oxygen. We can actually measure the oxygen in the stack and find out as to where exactly we are as far as the accessory levels are concerned.
Okay.
And so that way we are able to add one more dimension to the air to fuel ratio control. Something which was purely blindsided, we are now able to add the dimension of O2.
Right.
This is not something which happened now. We've been having it for a while now.
Yeah.
But that is added one more dimension which is very, very important because we are now able to in situ control the combustion based on even small little changes which happen in the atmospheric conditions.
Right.
Like I made a mention that the fan is a volumetric device. So stoichiometrically you require a certain kgs of air.
Right.
What the fan is actually going to deliver is a certain meter cube of air. So if there is a change in the atmospheric conditions, if the air is going to become hotter, then the same fan is going to throw in a lesser kgs per hour because the density is going to go down. And same way, if the temperature goes down, the fan is going to throw a lot more air than what is desired. All this is picked up by the oxygen sensor, and then we are able to get the necessary correction done in the body. So that is a practical aspect and a technological aspect which I think is important that people know. And those are the various means by which we are able to exercise control and operate it efficiently. As far as the safety aspect of it is concerned, we are able to keep very good control over the CO by ensuring that the excess air levels are maintained. So this is done right from the commissioning time up. But this apart, we also maintain a very good control over the pressure of the gas as it is going in. And then at any point in time, you always have a condition where you do not have fuel and air in the chamber where you have a stray spark. So we are talking about a backfire situation. So we are talking about a situation where you have a fuel and air mixing akin to IC engine, that is a limited explosion inside a boiler. That is something which is undesirable. So there are a lot of things like a pre-purge cycle, a post-purge cycle, which are built into the burner sequence control itself, wherein normal air is blown inside the furnace and the tubes to ensure that all the residual products of combustion basically are pushed out and we get a very, very safe atmosphere to work it.
Yeah, and the safety aspect is very critical, as you mentioned. It is an equivalent explosion, or at least a controlled explosion equivalent to an IC engine taking place inside the furnace, which is really going to be a problematic situation.
True. Yeah. In fact, if you look at backfires, backfires happen not only as a result of this, but there can also be situations where backfire happens because of let's say certain amount of issues creeping about in the fuel circuit also. So there are possibilities of leakages. So talking about gas, we have leakage detection systems also, which are installed in the lines, so that which even by mistake we do not allow the gas to get inside the chamber. And so even by error, we do not have a situation by which inside the furnace you have a lot of gas and then you have a flame which comes there by mistake, and then suddenly you have a backfire situation. So these are the things which are built in. There are a number of layers to this safety which we have managed to build in over a period of time, and that has actually held us in good stead. Accidents still do happen, but those are as a result of either carelessness, somebody does bypass something. Otherwise, modern day burners and modern day processes are such that we are able to limit any such eventualities by a great extent.
Well, that's interesting. And the automation, the level of automation that has actually benefited the optimization of combustion, that's really remarkable over at least a few decades now.
Correct. Yeah, that is correct. In fact, right now, I mean, if you look at the efficiency part, we have also got on to heat recovery units and all to add on to the efficiency. So we are running the ship. We are running really a tight ship.
Yeah.
I mean, if you look at it, so all developments with respect to burners over the last few years have been in instrumentation and in the safety loops. We have got into Serito, Sync3, as far as the instrumentation is concerned, as far as the burner management system is concerned. So all these are things which will really help, in my opinion, to benefit us over a longer period of time.